After, so
sounds like a case. Yes.
Hello everyone. Good afternoon and thank you for coming to this presentation. And this is our first seminar series of Trusted Networks Lab at PhD. And we call it Blockchain and Internet of Things, BiTS. And we plan to have this seminar every month. So we are expecting for this semester to have one next month in October, and in November, and then New Year. And we are very happy that Professor Juldrak will be giving this presentation on blockchain for sustainable lecture today. So without wasting any time, I'd like to welcome Professor Juldrak. Thank you.
Thank you, Sean, and thanks everyone for coming in today, as well to the people joining on Zoom. I see we have about 13 or 12 people on Zoom as well. So good to see people here. So as Sean mentioned, we'd like this seminar series to be an opportunity for people working in the blockchain and IoT areas in academia, industry, and government to have a conversation through this series and to make contacts to achieve impact together into the future. So we thought we'd start it and see how it goes. So, and I'm sure we'll tweak things as we go along. And what I'll be talking about today is our work on blockchain and cyberphysical systems. So what we mean by cyberphysical is whenever we have this tight coupling between the physical and digital environments. Now, this is achieved typically through sensors and actuators. Essentially, we're capturing the state of the physical world through the sensors, and we're converting it into the digital world where we can analyze it, reason based on it, make decisions, and in some cases take back action into the physical world, which is called actuation. So there's this very interesting feedback loop between the two domains that is enabled by cyberphysical systems. Now, the number of sensors that are out there these days, particularly in the Internet of Things, which is the underpinning network for cyberphysical systems, is growing quite rapidly. There are various estimates for how many there are in the world today, but it's certainly in the tens of billions of devices out there. And this really creates opportunities for new types of applications. Some people call it Industry 4.0. Some people call it the industrial internet, but essentially it's X 4.0. So there's opportunities in many application domains and industry sectors for making use of this technology to make more informed decisions, things like predictive maintenance, optimization of production, etc. But also alongside these opportunities, the sensors and all the data associated with them is really creating a flood of data. So depending on the application, you can generate many gigabytes of data per hour, say from a modern car or a jet engine. And this data really is creating challenges all across the pipeline, from storing, processing the data, communicating it to somewhere that can make decisions based on it. So while there are opportunities, there are also challenges with the volume of data. And this suggests that the common centralized approach to managing the data and the decisions doesn't necessarily scale in the world that we're entering these days. So typically there's a client-server mechanism where various clients connect to a central server to send their data or to get services. But that also means that there's a single point of failure and a bottleneck at that server. And also it means for the IoT devices that might be wanting to talk to each other to have some service or some exchange of information locally, they still have to go through that central server just because of the way the network has been designed so far. So other significant challenges with this centralized paradigm are security and privacy as well. So many of you will have heard of the Miraibotnet attack a few years ago, which had a distributed denial of service attack on many major websites, and that was done through very simple smart home devices that were compromised by attackers and told to send a lot of data at the same time to these servers, which brought the servers down. And we all know also that privacy is increasingly an important topic. There are a couple of PhD students in our group really focused on some of those aspects. A key, I guess, story that broke out there is the Facebook Cambridge Analytica scandal about how they used people's data from their profiles for influencing political elections. But what we also know is that these major players that hold our data are first creating data silos because they want to monetize the data and make use of it. But the data silos also limit opportunities for innovation and extracting the maximum value out of that data. What's more concerning is that when people give away their data to any of these centralized entities, they tend to lose control of their data and lose visibility into how it's being used for various services, whether it's marketing or monetization. And because IoT automates the collection of that data, it presents more challenges for privacy, because if you have things in your environment that are quietly collecting data about you without you even thinking about it, and that data holds privacy risks, then that can be a problem. So just to recap, there's quite a few challenges facing cyber-physical systems, from the heterogeneity of the device capabilities. We mentioned security and privacy and scale, centralization. There are poor implementations of security and privacy typically, because people typically prioritize, okay, we need to put these sensors out there to get us the data so that we can run our application. Security, we'll think about it later. Let's not worry about it now. And then the problem is that tends to create this legacy negligence regarding those considerations, which leads to some of the problems we're having these days. So in our research, we looked at, okay, what is the way forward? Is there another way forward to tackle these? And what we're looking at as a potential solution is blockchain. And that brings us to the title of the talk. I'm just wondering whether we can hide this Zoom header part, just for the slides.
I think you can click and drag it across.
Yeah, that's it. All right. So yeah, we're looking at blockchain as a potential solution to these problems. And I'm aware that in the audience, we have a diverse audience. So I just thought we'd cover the basics of what blockchain is. Now, blockchain is not necessarily a revolutionary technology from a computer science perspective. It's actually building on some well-known computer science building blocks. One of them is linked lists. That's a well-known, software engineering construct. The other one is asymmetric cryptography using private and public keys to share data across networks. Another one is hash functions, which take any input of arbitrary length, and then they can create a random fixed size output, which is quite useful for creating signatures of pieces of data. And then we have peer-to-peer networks, which again are a known computer science construct, which essentially, rather than going through that central server, distribute the communication and rely on that decentralized communication among the devices in the network. And finally, we have incentives, which is quite useful in blockchains, particularly monetary-based applications, so cryptocurrencies. And that was the first highly successful application of blockchains. I'm sure you've all heard of Bitcoin and the roller coaster rides of the prices and scandals and all of that across the news. But it's what we're talking about here is using the same underlying technology, but for non-monetary applications. So our goal is not to create a new kind of distributed currency, but to use this technology and its features for these cyber-physical applications. So if you wanted to think from a very high level, what those building blocks for blockchain provide is they move you from a centralized ledger or a centralized database to a distributed ledger. So rather than having one machine store all your data and you have to put all your trust and confidence in that machine, you then have a group of these machines that are maintaining a distributed database. They're all maintaining the same copy of the database. And every time anything needs to be added to it, they all have to agree. These validators that are now jointly managing the database, they have to agree on what needs to be added and who can add it. And that creates a lot of transparency and auditability in terms of not a single party cannot by itself just change the state of the database. It has to be agreed upon by all of these validators that are part of the network. And that's a powerful concept when you think about it in terms of the kind of services we access online these days. A lot of the big players at the moment are, whether it's central banks for monetary applications, but also the Ubers and Facebooks and Airbnbs, they're all centralized services. And they're essentially middlemen that connect people who are providing a service to people who are wanting to access it, and obviously taking a fee. But this conceptually provides a platform for decentralizing a lot of that so that the actual stakeholders can manage the networks themselves. And the question is, how do you do it? And the devil's in the details, of course, which is why we're doing research in this area. So we also need to have a word of caution that blockchain is not the silver bullet for any problem you might face. So there's a lot of work out there at the moment that's throwing blockchain as a kitchen sink on any problem and just saying that's going to solve all our problems. That's not true. And there are a specific class of problems that are suitable to be, for blockchain to be a solution for them. And there's this very famous decision chart by Wust and Gervais that asks you a bunch of questions about, do you need to store state, for instance? Do you have many entities that need to write, or is it all in one company that is writing? Do you have an online trusted third party? Do you know all the entities that need to write to the database? And if you answered, if you follow the top branch, then yes, you need a permissionless blockchain of the same nature as what is used in Bitcoin, for instance. But if you start going to the other branches, then in some cases, you don't need a blockchain. If, for instance, you don't need to store state, or there's one writer, then you automatically go to the decision point. I don't really need a blockchain. It's overkill for what I want. And there are some points in between where if you know the writers and depending on whether you need public verifiability or not, you can have a permissioned blockchain, which can be public or private. And that is depending on the application. Typically, permission blockchains are useful for enterprise applications where a group of companies want to work together, but they don't necessarily want to reveal everything to the outside world. All right, so also we explored this area, and Ali's here. He's the first author on that book, in a book that was recently published on blockchain for cyber-physical systems. And a lot of what I'll talk about today is actually building on that content from the book. So in terms of scalability, there are challenges for blockchain itself. So blockchain out of the box, if you take the Bitcoin blockchain and say, want to use it for cyber-physical systems and IoT, it's not, it has a lot of useful features, the auditability, transparency that we talked about, but it also has some challenges. And one of them is scalability. And the reason that blockchain can have challenges with scalability is that we said all these different machines need to receive everything and verify everything about the blocks because they're jointly responsible for maintaining that distributed database. And that creates a lot of overhead for those machines. And in order to maintain security on, for instance, the Bitcoin blockchain, we slow down the rate at which they can add data to the database. And that actually slows down the throughput. And what you're seeing in the figure there is comparing the Bitcoin throughput of 7 transactions per second to maintain that security compared to something like Visa that can process 24,000 transactions per second. So that scalability is an issue that requires investigation. And one of the reasons, or one of the consensus algorithms, these are the algorithms that allow the blockchain validators to agree on the current state of the blockchain. The most famous one is called proof of work, which is used in the original Bitcoin. And that one involves solving a cryptographic puzzle that's hard to solve, but then easy to verify if you've solved it correctly. So they end up spending a lot of computational power on solving this puzzle just to be the first to solve it and to add the next block to blockchain. In Bitcoin, the reward you get is you get Bitcoin rewarded to you, which these days is very valuable, even just one coin, we know that. But also it's a lot of wasted computational power that limits the scalability. And these days, Bitcoin mining energy consumes more power than 159 countries, including Ireland and most countries in Africa. So it's becoming a major carbon footprint on the world as well. So to address that, we propose a lightweight scalable blockchain, particularly designed for these large-scale networks like Internet of Things for cyber-physical systems. And we had a group of optimizations specifically for this context. So the idea of LSB is that it creates this overlay network that is the devices that might be routers or more capable devices in the network that manage the blockchain on behalf of all the IoT nodes that might report to them. And these are called OBMs in this figure. Now, the optimizations we have is rather than having a proof of work style consensus that consumes a lot of power and processing power, is we said, look, in IoT, typically, you don't have value exchange. You're mainly logging the data so that you can have transparency about what happened when. And issues like double spending, for instance, are not at the forefront as they are for cryptocurrencies. So because of that, you don't need the proof of work algorithm. And we replaced it with an algorithm we proposed called distributed time-based consensus. And I'll talk a bit more about that later, but the main idea is that nodes have to wait for a random time before adding a block. And there's neighbor monitoring to ensure nobody's cheating on that. We also added distributed trust to reduce the proportion of blocks that are cross-verified across the validators, and distributed throughput management as well. So in terms of the distributed time-based consensus, each validator can have one block per consensus period. And so there's one block per consensus period. However, there's a random waiting time before the block generation. So each validator has to wait that random time. And we have neighbors that verify that there's not just one validator that's trying to always sort of be at the front of the queue every time. And the way it works is, in this case, if the consensus period is 10 minutes, but here in this network we have a malicious validator that's trying to add blocks at a higher rate than that, then that gets detected by the other participants in the network that discard the blocks that don't meet that 10-minute period. So that's how the neighbor monitoring works. In terms of distributed trust, we made the observation that verifying all transactions in blocks is costly. And rather than doing that, as we do in our social relations, we can base the proportion of transactions that we have to verify on how much honest behavior we've seen from that agent in the recent past. And that's through direct and indirect evidence. So with direct evidence, if we've cross-validated or if we've seen direct evidence of the honesty of that agent, then we can be more confident that we can reduce how many transactions we cross-validate there, because we've seen that honest behavior. Indirect evidence is where one of our neighbors might vouch for a third node and say, I have direct evidence that they've been honest. But if we don't have that direct evidence, then we probably are more cautious in how much we reduce that validation. So we also did some simulations for that, and we looked at LSB versus a baseline blockchain, and we looked at this PTV, this gray line in the figure, is the percentage of transactions to verify. And what you see there is the timeline for the simulation from 1 to 60. And we see that the proportion of transactions to verify with LSB decreases over time as the nodes start gathering more evidence of the honest behavior of other nodes. So then that was about LSB. More recently, we proposed tree chain, which tries to take things to another level and tries to actually remove the competition from the consensus process. So the consensus process is typically all these validators trying to be the first, so that they can add the block. In tree chain, we actually endorse the idea that why don't we assign a different responsibilities to each validator so that things can happen in parallel, but that assignment is absolutely random, so that validators cannot try to claim or maliciously change part of the database. So essentially, tree chain is a validator selection algorithm, and the way we use a certain pattern that is randomized in order to select what is the responsibility of each validator for which blocks and transactions. And then from that point on, once that is picked, everybody shares that knowledge, and there's no dispute around that. So then we cut out that phase of trying to pick who's the winner, and everybody knows what they're supposed to do. And tree chain, it has a powerful element as well, in that most blockchains, like Bitcoin, for instance, Bitcoin blockchain, they have what's called eventual consistency. So when you have a transaction, you cannot be sure that it's been accepted. You have to wait for several more blocks to be mined until you say, okay, now it's deep enough that nobody can change this chain. Because when forking happens in the conventional blockchains, then you start looking at which one's longer to decide which one's the valid one. That's why you have to wait in conventional blockchains. In tree chain, because it endorses this idea of parallel ledgers, you don't need to wait for that time, and you have near real-time consistency in the ledger. And we mentioned the pattern, which is really critical for randomization there. And what we base it on is the hash function. So hash function is interesting because it's something that's already included and computed in current blockchains. So we're not paying an additional computational cost to generate the hash. Very briefly, hash functions allow you to take a message of arbitrary length and then have put it through the hash function to get a fixed length hash output. Its unique features are that it's random and that it's unpredictable. And it's already implemented in all blockchains, as we mentioned. So what that means is that by using this hash function to decide which validators get which transactions or blocks, they have no idea which transactions or blocks they will get. So if they were trying to, maliciously change some transactions or blocks that they wanted to target, they couldn't even pick them because they don't know what's going to be assigned to them. And so this is an example. What we do is we have a hash function output, which is of a certain length k. And so we assign a range of what we call the consensus code range, which are the most significant bits of the hash function output. And then each character, which is alphanumeric, essentially holds a weight. And we calculate, based on these weights, the key weight metric of each public key hash. The public key is what we use to identify each of the validators. So then what happens is if a validator has this public key, which is just alphanumeric, what we do is we use that weight dictionary that's provided there in order to figure out the key weight metric by taking the weights from that weight dictionary, adding them up. And then we rank, in this table, we're ranking the validators based on the descending key weight metric. And after that, we decide, okay, the one with the top key weight metric gets the first consensus code range, and so on. And that way, that mapping happens randomly. And that's then periodically changed. So periodically, these validators have to pick a new public key. The mapping is going to completely change in an unpredictable way. So that's about tree chain. And essentially, we found that it can achieve, on a Raspberry Pi, something in the range of thousands of transactions per second. And our estimate, we haven't implemented it, but on our estimate for a laptop scale computer is that it can exceed 100,000 transactions per second, because the speed of adding the transactions is just there's no competition happening anymore. It's mainly the speed at which the processing can happen to add those transactions. And there are other interesting elements there about communication and storage that I won't get into here today that also add to the challenges and the solutions. So that was about scalability. I want to move next to the memory footprint of blockchains. We get the question often, other than energy, what's this costing us in terms of storage? The Bitcoin blockchain has grown to be in the hundreds of gigabytes. But we also know for IoT, if you have all these IoT devices, these billions of them, generating transactions on a regular basis, this could become much, much larger. And so storing this data becomes more of a challenge, especially if it's persistent on the blockchain. So the immutability of the blockchain, the fact that you cannot change what's been added before, can be an issue, particularly with storage. And there's another challenge with storage. Many of you may have heard about the EU GDPR, which is also known as the right to be forgotten, right? So this is saying that an entity that has private data online about it has a right to request that data be removed. And it's mainly for EU citizens and companies, but any entity dealing with these people and companies as well. So it's almost everybody in the world has to comply with it. And that with blockchain, that actually creates interesting challenges in that once you put something on the blockchain, theoretically that's there forever. So what if you put something illegal or something that's threatening somebody's privacy? Then what do you do? Which is something that goes hand in hand with the storage issue. So we propose a work that essentially allows you to modify blockchains without breaking their consistency, because blockchains, essentially, people like them because they're immutable. So you cannot change the state of blockchain. It's handled by all these validators, but also that can become a liability at some point. So this approach essentially allows you to remove transactions from the blockchain without breaking the blockchain consistency. And we also had a conversation article about it around the time it was published. And the idea there is that we're keeping the transaction hashes consistent without keeping the transactions themselves. So we actually changed the way the Merkle tree is calculated, the Merkle tree root for blockchains. And the Merkle tree is a common construct that's used for all blockchains, which is a way to iteratively hash the content, so you can verify what's in there without having to go looking for it. We modified that so that from conventional blockchains, which is essentially they hash the combination of transactions together, we hash the transaction IDs. So essentially, we're keeping a breadcrumb trail of what data was there, but not keeping the data itself. And the value of that is that first, the data itself is private after that point. But also, if somebody in the future wanted to dispute something that happened, then you can prove that the data maps to those hashes that were left on the blockchain, because those hashes are fully consistent and stored immutably. And as long as the data you hold matches them, you can take it to court and prove that this was the data that was there, and prove your claims. So we also mentioned trust as a challenge for cyber-physical systems, particularly data-centered trust. So many people equate blockchain with distributed trust, say once you have blockchain, you can trust everything. And again, that's a bit of a myth, in the sense that blockchain gives you trust in the data you store, but what happened to the data before it got there is anybody's guess. And this is known as the garbage in, garbage out problem. So you need some additional mechanisms, particularly in cyber-physical systems, where you are getting data from faulty sensors or sensors that might be biased or have uncertainties in how they capture data from the physical world. How do you capture that once you store it on the blockchain and it becomes the gold standard? So that's a challenge. The additional challenge is, while we know that cyber-physical data is imperfect because of these considerations, we also might have malicious entities that are trying to actively affect that data for their own benefits. And these uncertainties get also mixed up. And if they get stored on the blockchain, you have some very interesting data with embedding all those uncertainties. So in that context, we proposed a trust architecture for blockchain and IoT. And the main addition there was to include a component that calculates the data trust. The idea there is that we have several inputs into what the data trust is. One of them is cross-validation of that data from other sources, for instance, sensors that share the field of view or some overlapping field of view with the sensor reporting that data. We also track things over time, so we have a reputation element for that data, for that particular sensor. And we also take into account the confidence reported by that particular sensor. I'll get more into that in the next slides. So the idea is you have a blockchain overlay network that could be IoT gateways that jointly organize a blockchain, but you also have sensors connected to each gateway that use the gateway to get to the internet. And the trust and reputation mechanism there is, it has those three elements. So the confidence is, if I'm a sensor and I'm reporting data, I say, how confident am I in my measurement? One really useful example of that is GPS, for instance. So GPS on your phone, it might have a ring around you in terms of where it thinks you are. That's actually the estimate of the GPS receiver of the uncertainty around your position. And other sensing modalities can also capture that uncertainty and communicate it. And that's the confidence element there. The reputation is the long-term reputation, as we mentioned. So how many times in the past has this sensor checked out in terms of the kind of data they provided? And finally, the T-sense is the evidence from other observations. So for instance, in a localization example where I have a lot of sensors in this room telling me, for instance, Daniel is in this room. If one of them is saying Daniel doesn't seem to be in this room, then I actually won't trust that one, because all the others are telling me that he's in this room. And obviously that's a sort of a binary, but you can look at it in a continuous sense when you have signal strength, for instance, coming from these devices. So that was about the challenges that we had, that we looked at for blockchain in CPS. And these were the horizontal elements about trust, scalability, immutability, storage optimization. We also did have some work on anonymity that I'm not getting into here today. But we also, over the last several years, we looked at different vertical applications, including supply chains, connected vehicles, energy trading, and manufacturing and digital twins. And I'll get into some of these just from a high level in the remainder of the talk. So in terms of supply chains, what we first looked at was product chain, which was, we wanted a way for like design a blockchain architecture that supports provenance in supply chains. And what we mean by provenance is we want to know where products came from and the journey they've been through. And that first work was proposed a consortium blockchain architecture that had introduced the access control rules. It also introduced the transaction vocabulary, so identifying transactions for how you use transactions to say a product has been created by a farmer or transferred among the different stakeholders in the supply chain, or combined with other raw material to produce something else. And then we have the network model, which defined a global blockchain, but also side chains to provide a bit of scalability that can be managed across different geographical regions. So once we had that provenance element, then we started, actually, I'll give that example here. So if you had a bar of chocolate and you wanted to work back of what happened to that chocolate before it came to your hand. So the way this product chain would work is you'd submit a query, and then that query would go backwards into the transactions that for this product in its story, and it would reach a point here where at the manufacturing stage it was combined between the cocoa beans and the milk. And so that branches off, and again, working back through the transaction chain, you can go back to that this was produced by dairy farmer Bob, and cocoa farmer George is the one that produced the cocoa beans. So that's what product chain provides. So after that, we looked at trust. So as we mentioned before, generically, trust is a key issue. The main problem with supply chains with trust is if a supply chain entity tells you, all right, I've stored this piece of meat at the right temperature, how can you trust that? Even if the sensors are telling you this temperature was maintained, it's obviously in that entity's interest to tell you, yes, my products are the best. So, and similarly, other kind of observations, it applies there. So we realize that there's a lot of this data going into supply chains, but we want to add to the trust that we have in it. So in this architecture, we have these multi-source data observations, which could be sensors. You might have random checks from regulatory bodies. The traders themselves will give an indication of, all right, you gave me this product, I think it's really good quality, or I think it's so-so. And that also all feeds into the data layer. But then at the blockchain layer, we added a trust and reputation module that maintains over time how honest a trader has been, or the level of quality of a particular product. So there's reputations and trust for both products and traders as well. And then we have the application layer that where you can have queries and rewards and penalties for good and bad behavior, respectively. So after trust, we also looked at privacy, because we realized that all this talk about sharing everything in a supply chain is great, but in a commercial scenario, many entities will not want to share a lot of their data for competitive reasons. So the question we looked at here was how do we balance that trade-off between the privacy and the transparency that's needed? And what we came up with was to use zero knowledge proofs. So essentially, if I'm a wine producer in a highly coveted wine region in Australia, but I don't want to give away, for instance, the farm where I produced my wine, I just want to say it's from South Australia in this region. So you can prove certain attributes about your product without having to share the raw data. And this is also tied to incentives through a commitment scheme, so that if you the entities that are contributing to proving that that attribute actually get rewarded in the system. So that was a way to prove certain attributes about traders without them giving away all their data. We also had another approach to privacy called trade chain, which separates the ledgers that are managing the identities of the traders with the ledgers that are managing the trades that the traders are doing. And we have a smart contract that through a token-based approach manages access to certain information on the trade ledger, but the traders can maintain privacy on their identity when they choose to. All right, so that was about supply chains. Next, I'll move to connected vehicles. And as for many other applications, there's a lot of data that's coming from connected vehicles. With 5G, people are talking about vehicle-to-vehicle connections, vehicle-to infrastructure. We have electric vehicles coming into the mix and all their diagnostic data. So lots of data coming up. Autonomous vehicles produce a lot of sensor data as well. So that also, the vehicles highlight the security risks in a major way, because if you compromise a sensor in your house, people might know that you're in or out of the house. But if somebody takes over your vehicle, which has been demonstrated by some white hat hackers, then they hold your life or death in their hands right there and then. So we proposed a blockchain approach for automotive security and privacy. This largely built on the LSB architecture, where you have these capable entities managing the blockchain, and vehicles can move between different clusters in the network and adding their transactions there. And one example application that we looked at was when you have a wireless remote software update for a vehicle. So in this case, you have a software provider that came up with the update and wants to send it to the vehicle. Now, the vehicle's purpose is to make sure this is a genuine software update that's not going to disadvantage it in any way. And what happens there is that the software provider would provide an update to a cloud storage, and then it would send a multi-signature transaction to the overlay network. That is then broadcast and sent around in the overlay network until the node that's responsible for the vehicle manufacturer is found. That manufacturer then countersigns the transaction. So to say, yeah, this is a correct update that the vehicle should install. Once that is countersigned by the manufacturer, then that is sent as a notification to the vehicle so that the vehicle can access that particular software update and download it. So that's one example of how we use that approach, that blockchain-based approach in automotive security and privacy. We also looked at the interesting problem of particularly when autonomous vehicles have an accident, who do you blame? Do you blame the manufacturer, the software provider, the most recent service technician, or the owner? And obviously, these entities will want to shift blame because they don't want to be liable for that. And in this work, we use blockchain as a immutable data repository where you could store this data about the vehicle's driving behavior and accident data, both from the vehicle and from neighboring vehicles that are witness to an accident, which we call BFICA there. And the idea was we used two different blockchain partitions. One where you have the operational entities, the vehicle, the service technician, the manufacturer, that were jointly maintaining the blockchain. And basically, that's the accepted state of the vehicle. And you also have a decision partition that when there's an accident, all that evidence is sent from the operational partition to the decision partition to decide, okay, based on this evidence, who's liable. And the decision partition, the members there are the government, transport authorities, legal authorities, and so on. And so an example scenario for that is when these 3 autonomous vehicles at the bottom have an accident, they each send either their primary evidence of what they say happened, but also any witness accounts if some were nearby. And in this case, they happen to be on different partitions, operational partitions. Potentially they're with different companies or in different, like their home area is different. So they send that information, that's mined into the blockchain, and then all that evidence converges on the decision partition that makes a call on who's to blame. All right, the last application I'll talk about is energy trading, and that's quite an interesting one, given the current issues about climate change and the like. So we have an increase in renewable energy sources, and in Australia we're lucky to have the sun and the wind, and we know that household solar penetration in Australia is quite high. I think it's somewhere around 25 or 30% across all Australia. So that's really an opportunity for reducing carbon footprints and being more sustainable into the future. Now, to incentivize people to take up these technologies more, energy trading can be useful. Currently, in Australia, you have this feed-in tariff where you, if any excess solar, for instance, that you have from your household, you can sell back to the grid. But the original grid architecture was designed in a centralized way. So you have an energy company that's typically managing all the information and all the power distribution, which again brings back the challenge of centralization. And also you're giving away a lot of your smart meter data to this company that can infer a lot of things about you. So in this work, we looked at blockchain-based energy trading, which has its own challenges in that a lot of the companies that were, there are some companies out there doing blockchain-based energy trading, but many of them still have either a centralization at the trusted third party, where that company wants to be the owner and center of trust, which is interesting because to some extent, it goes against the philosophy of having a blockchain. But also, when you have that give and take, you're giving away some private information when you want to sell or buy energy, which can be used by malicious parties. And then there's a blockchain overheads about storing all the transactions for negotiating energy trades. So in that context, we proposed this secure and private blockchain for energy trading. And it had 3 elements. One was an anonymous routing backbone that can route information in the network, not based on IPs that give away your identity, but based on public keys. And another one is the introduction of atomic meta transactions, where we reduce the transaction overhead of negotiating or buying and selling energy. And then there's a private authentication method to verify smart meters. So the anonymous routing backbone essentially uses public keys for routing data in the network. So you have these backbone nodes that are each responsible for a range of public keys. Conceptually, it's similar to tree chain in a way, but this is mainly for routing. And then you have, whenever you want to send information, you send it to the router, which is the node that's the backbone node that's responsible for your public key range. In terms of the energy trading process, so typically the issue there is you want to make sure that the buyer pays and that the seller provides the energy. And what we do there is combine these 2 elements into what we call a meta transaction, so that when the buyer commits to pay, it sort of locks those funds in their account until the seller provides the energy that you can then close the loop and transfer the money once everybody's confirmed that they got what they expected. And then this certificate of existence, which the idea there is that if you have distributed energy trading, you might have many entities claiming they have energy to sell you. But how do you verify that they're actually genuine smart meters, those entities? So the idea there was to have this anonymous verification that that remote entity is a smart meter. And the way we do that is we actually ask another random smart meter to verify that our public key, which we're using, is actually issued by the manufacturer, and that random smart meter vouches for the authenticity of the smart meter that's offering the energy. And we call this the certificate of existence that a seller can then share as proof that it's been verified by this random entity. The reason that other smart meter is random is that then it doesn't favor any malicious entity that might want to try to get there in the middle, and it maintains anonymity as well. And then more recently, we added location awareness to this. So one observation is that in energy trading, particularly if it's distributed, you want to incentivize entities to trade with nearby smart meters, because otherwise it's much more overhead on the grid. It's not in anybody's benefit to trade very far away. So we came up with a decentralized market clearing. So basically, you have these offers and negotiations of energy going on. But to enable that location bit, we introduced a novel proof of location, anonymous proof of location approach, where you could verify that a smart meter is nearby, so that you can incentivize that transaction to happen. So the concept there is very similar to what we did in certificate of existence, but here we are getting a certificate of authority to verify the location. And that could be the grid provider that actually knows where all the smart meters are. But it's also happening, the selection of the verifier smart meter B, happens randomly. And it happens in a way that's transparent to smart meter B, so that smart meter A can use that as a certificate of location for its trading. And then what we found in some of our, this was a collaboration with Monash University, from people from electrical engineering there. What we found is that this approach tended to incentivize the smart meters to trade with smart meters that were more nearby, because it cost less and it was more efficient for them. So that really concludes the talk. I just want to probably wrap up by saying there's lots of exciting opportunities there, and I want to thank also the many contributors to the works that I talked about today, both from QUT and from other universities. And we'll probably share the video of this, so you'll be able to look at the references if needed. And thanks everyone for listening.
Raja, I guess one of the things that is obviously different in a distributed system or decentralized rather than a centralized system is the sort of business models that will operate. And you talked about a number of cases where there has been an attempt by the commercial interest to centralize some function, which is, as you say, not in keeping with the whole blockchain concept. How much work's actually been done around business models that will work with a blockchain type concept?
That must be. So I mean, definitely even the cryptocurrency work is already, the business model is somehow embedded in the reward, so that the computers and owners of the computers that manage the network get the rewards through that cryptocurrency payments. Now, it's a very good question in the sense that in non-monetary applications, what are the incentives, right? Somebody is going to spend compute power in order to maintain that blockchain. What do they get in return? And there are some ideas on whether they get tokens that can be used for other purposes. In this ecosystem, you can create tokens that don't necessarily have to be monetary, but can be used in an ecosystem. to access certain services or to get discounts on certain things or to get advertising rights, for instance. So there are, but it's certainly an interesting area of work that's probably more on the economics side of it and potentially some game theory. I can't say that we focused on that to a large extent, but there is some work going on in those communities.
I'm curious about the concept of trust. It seems that the most common implementation is consensus. You trust something is true because everyone says it's true.
Yeah.
You can imagine a situation where, particularly in IoT, where maybe all sensors are equally being affected in a negative way. And maybe the majority of them are saying something, but there's one or two good sensors that always give the right answer. Is there any work being done on maybe assessing the statistical reliability of a sensor rather than just taking a broad consensus?
Yes, there is work going on people sort of take the statistical distribution of what you expect to see from measurements of sensors and compare it to the current distribution of measurements, and that can speak to is the sensor, is it capturing things that are expected? Now, when anomalies happen, when a huge event happens that is true but is changing the state of the world, it's hard to necessarily capture that through that distribution. And you're right, the collective acceptance of the state of the ledger is not the ground truth, right? It's just the accepted state voted by the majority. So the solution needs to be a combination of these, the statistical aspects, the cross-validation, potentially some external observers bringing in their input and being in the loop. And that's what science is, right? We're trying to get to the truth, but we know everything we have is observations that are getting us closer, and we need to know how much we can rely on them.
By asking the question, do I get contributing author status on all subsequent papers?
We can talk after.
Audience. So thank you very much.
Imran.
Oh, okay, sorry.
Thank you very much for a very nice presentation. Of course, IoT and blockchains, these technologies, they are looking very fascinating. Don't you think that probably we will have some hard time where, on one side, governments, they want to control everything. They want everything to be controlled by them. On the other hand, blockchain and these technologies, we are talking about distributed things. So don't you think regulating these technologies will be a big challenge for the governments? And if there are some regulatory laws, for example, this GDPR, and when they came in, companies like Google, Facebook, and they had to face a very hard time, and they are still facing a lot of penalties from the courts. So exactly, don't you think this is going to be a big challenge from the regulatory side?
Yeah, that's a very good question. I think, so this is a network technology, right? And in networks, if you leave them unconstrained, what will happen typically is you have the preferential attachment, you have the big players. That's what happens on the internet and in business networks as well. I think in terms of regulation, you're right that it is a challenge. Blockchain presents a challenge for regulators. I think also that in some ways, sometimes government is looking at it as a way to work hand in hand with regulation. I'll give you an example. The Australian government recently put out a call for tender for funding for 2 pilot projects. Both of them were to reduce the regulatory burden of, one was for rare earth metals, the other one was for food and beverage using blockchain. So they're saying, okay, there's too much, paperwork involved in getting approvals and in certifying certain things about these products. So can we reduce that red tape and regulatory burden with blockchain? I think having many of our current systems running pure permissionless, distributed, open public blockchain is not realistic. But I think because we have that spectrum of permission, private and public, or permissionless, many applications will find their home somewhere in the middle. For instance, supply chains can use enterprise permission blockchain and consortium blockchain, whereas that provide that good balance between the ability to regulate, but also the ability to to transact more freely in a transparent way.
Hi, I'm Craig O'Kane from Everledger, one of those companies that has won the Australian federal government pilot to build the blockchain for critical minerals.
Yeah.
And we're exploring that at the moment. So I just wanted to mention that, but also thank you very much for your presentation. I think from our perspective, we'd be delighted to continue the conversation with you as we build that pilot out, possibly with a conversation, if you'd like to, with our CTO in California.
Yeah, that would be great. Yeah, and I've had the previous discussions with Leanne, and I think we had, was it your CTO or one of the members of your executive on a panel not long ago? But I'd be very happy to have those conversations. Maybe we can talk after this.
Thank you. Any other questions? No, I think we have one chat there.
Yeah. It's not a question. Yeah.
Any question from,
Yeah, thank you, Katrina and Harry and Doug.
So I think thank you everyone for coming today, and we'll upload this presentation to our Trusted Networks Lab website. And we are having our next seminar organized on 6th of October next month, and followed by last one for this year on 10th of November. So we will keep posting through emails. And thank you once again for coming today. We have launched served outside. We have a list of options from vegan, vegetarian, gluten-free. So please feel free to have anything from there. Thank you all.